September 12, 2025. Astronomers spot something that shouldn't be there. A colossal object tearing in from deep space, its tail stretched across the sky like a banner, 5 full moons wide. Within hours, a second intruder is confirmed, racing toward the sun from the opposite side of the heavens. 2 newcomers, 2 angles, 1 narrow window. The official explanation says twin comets. The numbers whisper something else, something timed, deliberate, engineered. Is this an interstellar accident, or the opening move of a mission that started long before we were paying attention? Stay with me, because the energy figures on the big one will upend what you think is possible. The first detection freezes the team at the console. A solar watching instrument flags a new object, bold enough to leap off the screen. C/2025 R2. Soon everyone just calls it SWAN. The data pours in. Its tail spans about 2.5 degrees of sky, roughly 5 full moons edge to edge. That scale is unheard of for something so newly found. Early brightness estimates hover around magnitude 7.4, bright enough that backyard telescopes and even binoculars from a dark site can pick it out. 2 days later, an Australian amateur captures a frame where the streak nearly spills out of view. By September 13th, the name is official, the designation broadcast, and suddenly half the planet is pointing lenses and dishes at the same target. The reaction isn't just excitement, it's disbelief. Modern comets usually start faint, grudgingly giving up their presence to larger observatories. SWAN arrives like it owns the inner system, gliding through Virgo, brightening as it closes the gap to the sun. The community begins a familiar dance: measure, debate, remeasure. But the scale refuses to fit the old steps. It looks less like a dirty snowball and more like a searchlight. The question changes from "what is it?" to "why now?" And then comes the second thread in the braid: 3I/Atlas. This one was already inbound before SWAN was flagged, but from a completely different corner of space. Trace the paths on a star map, and you see arrival vectors separated by more than a quarter of the whole celestial sphere. They are not neighbors, they are strangers converging on the same intersection at rush hour. Their closest approaches to the Sun, perihelia, are scheduled within the same 10-day window. Atlas around October 17th, SWAN around October 20th. One skims at about 203 million kilometers, the other at roughly 150 million. Their closest points only about 50 million kilometers apart. Closer than Mars ever gets to Earth. This isn't just overlapping dates on a calendar, it's geometry. Both orbits are steeply tilted. SWAN more than 60 degrees off the ecliptic plane. Atlas nearly perpendicular to it. Their approach angles are so different that the odds of 2 bright objects hitting nearly the same distance from the Sun, within days of each other, is painfully small. In the language of orbital dynamics, this is a corridor, a narrow window in space and time both bodies occupy together. Coincidence remains a possibility. You can never completely rule it out. But even the skeptics pause when the lines line up this cleanly. Then the timing throws a new punch. From October 8th to October 18th, the Sun's glare blinds ground-based telescopes. It's solar conjunction, a built-in blackout where the brightest light in the sky drowns everything near it. The critical days, when both objects hit peak heating and any anomaly would be most obvious, fall right inside that blind spot. You can write it off as bad luck, or you can call it what it looks like. The perfect moment to act without witnesses. Atlas makes the first strong case for not normal. Not because it shines, because it misbehaves. Early spectral reads hint at a nickel-heavy signature with almost no iron, an upside-down ratio for typical comets. Then the gas mix comes back odd. The coma's carbon dioxide outflows dominate, showing up at roughly 5 times the rate of water vapor. Strange, but maybe not impossible. What isn't easy to shrug off is the motion. Observers logged 3 distinct accelerations, each about 2 weeks apart. Each jump coincides with a change in tail color and a flicker in brightness. The pattern is stepwise: a kick, a glide, a quieting, then another kick. It's the kind of curve you'd expect from a thruster, not from sunlight slowly cooking pockets of ice. Skeptics demand calibration checks and control runs. The teams go back to the raw data, scrub the instruments, cross-check against independent stations. The pulses keep showing up in the same places on the timeline: late July, mid-August, and 2 weeks after that. If those accelerations are real, the implied power from inside Atlas lands around 10 gigawatts. 10 large nuclear plants worth of shove, inside a body we'd normally call a snowball, with delusions of grandeur. You can hear the word they don't want to use, circling the conversation anyway: propulsion. If Atlas is a drone, quick, responsive, economical, SWAN looks like a fortress. Everything about it is scaled up. The tail that drags half a constellation behind it, the steadiness of its brightness, the way it refuses to crumble as the solar wind hammers it. Some reflectance measurements suggest a sharp metallic edge. Amateurs whisper nickel cobalt, the kind of alloy we choose for strength and corrosion resistance. Around the nucleus, processed frames show a persistent silvery glow. Not the fuzzy fan of dust, but a halo that shifts and tightens like a shell of charged particles. The phrase plasma envelope starts appearing in late-night chats and early morning emails. Then there are the tiny wobbles. Photometric analysis picks up micropulses, minuscule rhythmic changes in the tail's direction, as if SWAN is making course corrections with millisecond bursts tucked inside the turbulence. Stack that with the energy estimate some models spit out if those pulses map to thrust, and you arrive at a number that makes your stomach drop. On the order of 10,000 gigawatts. More raw power than Earth's entire electrical grid. If that sounds impossible, you're not alone. But the math is simple. If a massive object changes its path on a short time scale, something big pushed it. Nature can push, so can design. The orbit adds a haunting footnote. SWAN is on a path that loops back every 22,554 years. Its last close pass would have been when ice sheets still smothered half the northern hemisphere. If SWAN is engineered, someone set a timer longer than recorded history and let it run. And somehow, that cycle brings it into the Sun's neighborhood now, at the same time as Atlas, during a blackout that hides the most critical hours from most of our eyes. What could they be doing? 3 mission profiles make the rounds. The first is almost boring by comparison. A solar pit stop. The Sun is the best power source in a few light years. A smart probe could dip into charge, skim magnetic fields, dump data to a sibling, or even audit its own systems under controlled stress. Humans do gravity assists. A better civilization does energy assists. A rendezvous in a tight corridor would make sense if timing matters for the handoff. The second is less friendly. An intervention. Imagine Atlas has a fault. Guidance, memory, power. SWAN The heavyweight arrives as the service tug, the rescue ship, or in a darker version, the enforcer sent to shut a malfunctioning asset down. Stepwise accelerations in Atlas look like active maneuvers. Microthrusts in SWAN look like course trimming. Meeting in the glare would be an elegant way to stay unobserved by a planet full of curious primates who think every light in the sky belongs to them. The third is an audit chain. We've been leaking radio and radar for more than a century. In 2017, something long and dark drifted past. Oumuamua. Too fast for our nets, too late for a close look. Then Atlas, lean, rule-breaking, almost cocky. And now SWAN, bright, armored, unhurried. 3 notes in a scale that climbs. Each pass closer, each pass more capable, as if someone is tightening their focus dial with each try. If that's the pattern, the sun isn't a backdrop. It's the beacon all of them steer by. Deep time creeps in at the edges of the story. A period of 22.5 millennia presses against the end of the last ice age, when climate whiplashed and the first monuments rose. People point at ancient stones and see star maps. Sites like Göbekli Tepe, with animal reliefs and abstract marks that might be calendars, or might be metaphors we no longer understand. Mainstream scholars warn, rightly, that connecting carvings to specific cycles is speculative. Still, the timing refuses to let go. If a bright long-period visitor returns on a schedule so long no one human could witness it twice, where would you keep the memory? In stories, in rituals, in stone. While the public story sticks to bland schedules and standard blackout warnings, the back channels tell a quieter tale. During conjunction, some requests for high-resolution imaging and radar pings go unanswered. A few proposals for alternative coverage vanish into a folder with no name. It could be bureaucracy doing what bureaucracy does. It could be something else. Either way, the big mirrors pause, and the people with the smallest telescopes decide not to. The amateur mesh becomes the lifeline. Open-source orbit calculators hum. Backyard astronomers sync timestamps and trade raw frames before compressions wash away the details. Small radio dishes listen for the sun's whisper bouncing off tails, looking for flickers that don't belong. A weather satellite nobody looked twice at becomes a stopgap eye. The best thing about a distributed network is that it's hard to silence. 1,000 little apertures are louder than one big one. If a post-blackout anomaly shows up first, it might appear in a forum post from a garage, not a press conference from a lab. And then we wait. The corridor closes, the sun moves on, and both objects slide back into a sky we can finally see. If Atlas lights its steps again, if the tail swings in those clean little pulses, that's a data point. If SWAN's halo tightens when a solar gust hits, that's another. If they angle toward each other, or away, that's a third. Science is a stack of ands. This, and this, and this. Enough ands become a story you can't ignore. So what are we left with tonight? 2 anomalous visitors, one slender, rule-bending, possibly nickel-rich and thruster-brisk. One massive, bright, resistant, possibly armored, wrapped in a whisper of plasma, cruising on a 22,500-year loop. Opposite entries, synchronized perihelia. A blindfold exactly when the show peaks. Call them comets if that helps the nerves. Call them probes if the numbers make you brave. Just don't call their timing ordinary. When they emerge from the sun's glare, pay attention to 3 things. First, the pulses. Does Atlas jump in steps again? And do those steps line up with changes in the tail's color and brightness? Second, the halo. Does SWAN keep that silvery skin, shifting and tightening like an electromagnetic shell? Third, the choreography. Do their paths treat the inner system like a meeting point, or just a shared hallway? The answers won't settle everything, but they will narrow the map from a galaxy of maybes to a few sharp lines. If there's a plan here, it started long before our first radio went live. If there's no plan, then we're witnessing one of those rare coincidences that trick the human brain into seeing intent. Either way, the sky is telling a precise story. Two objects, one corridor, a blackout at the peak, and a planet full of watchers learning that sometimes the most important part of a mystery is the part you aren't allowed to see. Keep your eyes on the data. Keep your mind open. The next frame could fall to a backyard telescope or a deep space dish. And when it does, the difference between comet and something else might be just one more pulse in the dark.